Alright, this problem is probably even more important than the pyramidal tank. Probably. The reason I say that is because before I even read the question, I'm going to talk about the way this shape works in terms of similarity. Now, this tricked me last year this problem type tricked me last year when I got it, but it will never trick me again after that. Now, the issue with this compared to like the last problem we did, which was a pyramidal tank, is that if you watch how height increase, like what happens when height increases to the other variables, sure, width increases, but this length is going to stay constant throughout, which means that height is proportional to width, but height is not proportional to length, which means when you're setting up your equations, v over v1, you're actually going to get h squared, because of this part, times L over h1 squared times L, where L are now part of the constants, and those cancel out as well. So you're going to end up with h squared over h1, that should be squared, h1 squared. So that's the premise. Now, I definitely recommend pausing here and trying this. Oh god, I'm nasally, using what you know, but I will be going over it. Wow, why am I so nasally? I hope I don't sound like a nerd right now. It's because of allergies. Okay. So I'm going to write that off to the side. V over V1 equals H1 H squared. Oh god. And remember, that's because there's one constant. This gets a lot of people, including me. A trough shaped, I have no clue if I'm saying that right. A trough shaped as an upside down triangular prism has a constant length of 20 units. See, constant length. I think I actually specifically stated that so that to try to trick people as little as possible. The initial one did not say that. Water fills up the trough to a certain height of 5 units. The rectangle formed by the surface of the water at this time has an area of 200 square units. The water level then continues to rise, still contained by the trough, until the rectangle's area has increased to 400 square units. What is the volume of water in the trough after this increase? Okay. Step 1, find the initial volume. Oh, you know what I forgot to do is talk about my starting point and my ending point and how I know where to go. So I'm going to do that here. I am given my constant length equals 20, and I'm given a certain height, which equals 5, and I'm given a rectangle formed by the surface of the water is, what is that? Oh, 200 square units. Area at the top is 200. Now, this area at the top is represented by that. That means that we know L, we don't know width, but we know the area, which means we could solve for width. What that allows us to do is that because we're looking for the volume of the water, we need width to find the volume of the water, the initial volume of the water, just to set this up. So that's what we're going to do. Just to set up this thing, we're going to find the width of that initial instance. Length is 20. It's going to be triangular prism, which means it's going to be the triangle part times h times w times the constant length. Now, we can solve for width by saying that 200 equals length times height, not height, w, width. 200 equals 20 times width. That means 10 equals width. Hope that makes sense. 10 equals width. From there, this equals volume. 1/2 times 5 times 20 times 10. That did not write down 10. What is up with that? equals volume initial. I'm going to go like that to get another 10. That's just going to become a 10. And you get your volume to be equal to 500. That's your initial volume. Remember, the reason we did that is so that we can set this up. We've got a height. We've got one level and continues to rise. You know what I just realized? So I forgot I did this. It doesn't really matter, but I made this equation in terms of height. It actually gives us... Wow, I made this a little bit trickier than I thought. Bravo to me. It gives us how the rectangle's area has increased. It does not give us how the height has increased. The initial question didn't actually do this. I think it just told you how the height changed. But remember, the length is constant, meaning that length is constant, meaning the change in... Sorry, that length I meant. The change in this rectangle's area is specifically due to this width, meaning what we really should be looking for is this. Now, I'm sorry I didn't make that apparent before. I didn't fully read or I read it out loud, but I didn't really fully take in what it was saying. But that's what we should do. Now, we can set up our equation. Oh, what the hell? Still getting used to this. We can set up our equation because we know the initial volume and the initial width is 10. But we can't solve this right now. What we have to do is we have to take the fact that we know what that top rectangle's area has increased to, and we know that the fact that the length is constant to solve for W1. The rectangle's area is 400, and we know that rectangle equals length times width, so that's going to be length equals 20 times W1. Solve for W, and you get 20. Now, pretty simple from there. I'm going to rearrange. Equals 500 is going to come underneath, and you get... Sorry if this doesn't make any sense, just pause for a second and read it over. I just did a bunch of mental math for no reason. Mental gymnastics. Okay. That doesn't look like an integer. What is the volume of the water in the trough after this increase? That might be. Is that? No. 1 second. What did I do wrong? My favorite game. What did I do wrong? That increased to that. Okay, I honestly probably just did some mental math wrong. Let me do that out. We're gonna multiply both sides by V1. You get 500 equals 10 squared over 20 squared V1. And 20 came from here. Now 500 times 20 squared over 10. Yeah, this is why, guys, do not do me. Do it out, please. This makes way more sense. Anyway, from there I'm going to do what I love to do and say that this is equal to 5 times 10 times 10, 500, times 2 times 10 times... Actually, that part's unnecessary. We already have the 10 times 10. So times 20 squared. 20 squared is just 400 over 10 squared. These cancel. 400 times 5. That is definitely a number. That is a nice number, actually. So that's how you do that problem. It is very interesting, and honestly, I kind of regret putting this on a timed practice, because this problem probably would not be on the actual meet, because it does a decent amount of gymnastics. But it's still good to understand, especially, this is the main part. Oh god, this is the main part you should get out of this, and how it works. The surface area stuff was kind of like extra bonus points. Like, I think it's cool, but I did not realize that